Hello, everyone. Welcome to the first session on chemical engineering thermodynamics problem solving session. So, this is the instructor is Professor Shashidhar Guma from IIT Tirupati, and I am Namrata Kulkarni, PhD scholar from IIT Madras. So, these sessions will be conducted every Saturday from 3 to 5 p.m. So this will be mostly tutorial kind of sessions where we will solve different sort of questions, and also we can have a doubt gets cleared whatever you have from the last week, and you can ask anything from the subject. So I hope you have gone through all the videos in the course for the last week, and also assignment 1 is active now. You can see that there are lecture notes for every week, so you can download them, and this will cover whatever has been taught in the following week. So I hope you have gone through that. So starting with this, in thermodynamics, generally there are fundamental properties of any system, temperature and pressure. And this temperature has different units, Fahrenheit, Rankine, Celsius and Kelvin, and these are interchangeable, like you can convert from one unit to the another. And the second one, pressure, has different units like Pascal, which is a SI unit, bar, which is 10^5 Pascal, torr, which is actually 1 mm of Hg, the mercury. So in most of the manometers, what we use in industries and everywhere, labs, mercury is used for measuring the pressure difference. And atmosphere. And we need to know that generally we measure the pressure differences between 2 points. So we need to add, that is a gauge pressure. We need to add the atmospheric pressure to get the absolute pressure. So in all the thermodynamic calculations, we use the absolute pressure there. So coming to the questions, the first question is, pressures up to 1000 bar are measured with a dead weight gauge. Okay, so this much pressure is being measured. The piston diameter is 4 mm. Okay. What is the approximate mass in kg of the weights required? So in here the pressure till 1000 bar can be measured. So what can be the weight here? Okay, so generally what we know, the force balance here is total pressure up. Okay, uh, okay, consider this is the pressure P absolute here. Okay, P absolute is equal to P gauge plus P atmosphere. Okay, generally F is equal to MA is equal to mg here. Okay, that force and the atmospheric force both will be there. So on equating the force balance, we get by cutting off the atmosphere on both sides, we say mg is equal to the pressure inside this system into area, which is pi r square, which is also equal to 1000 bar into pi d square by 4. Okay, you need to note that this is the diameter. And this bar has to be converted into SI units so that we can get all the things in SI units. Okay, which is 10 power 5 Pascal. And here the G is 9.81 meter per second square. Fine. So on doing this, on this calculation, we get M is equal to 128.09 kg. I hope that's clear. And this D is also has to be sorry for that. Okay. So this D is 4 into 10 power minus 3. Okay, meter, all in the SI units. Second question is at 27 degrees Celsius, the reading on a manometer filled with mercury is 60.5 centimeter. The local acceleration of gravity is 9.784 meter per second square. To what pressure does the height of mercury correspond? So, generally, a manometer with a mercury, assume there is 0.1 where P1 is there and P2 is there, okay? Like this. A manometer is there, okay? Assume here the height is this and here the height is this. Okay. Now P2 is greater than P1. Assume that, okay? Now we say here the pressure is P1 by Pascal's law. Here pressure is P2. We say here both are equal. So, and this is delta H. And this is mercury. So mercury, we have the density is equal to rho 1. Okay. Rho is equal to 13.53 grams per centimeter cube. This is a very well-known density, and like generally everyone knows. So we can say P1 plus rho G delta H is equal to P2. Therefore, the delta P is equal to 13.53 grams per centimeter cube into 9.784 meter per second square into 60.5 centimeter. Right? Here we get centimeter square and this gets cancelled. We now want to convert everything into same units. So 13.53 into 9.784 into 60.5. Okay. Into 1 by 10 power minus 4. And this meter square. So turns into meter. And this gram needs to be converted, right? So into 10 power minus 3. Okay. This is kg per meter second square. It's equal to 80090 kg per meter second square, equivalent to 0.8 into 10 power 5. This kg per meter second square can be expressed as kg meter per second square by meter square. Okay, so this is Newton and this is area, right? So Newton per meter square, which is Pascal. This all is Pascal. And 10 power 5 Pascal is 1 bar. So I say 0.8 bar. Okay, so with this question, I wanted to point out on the fact that this pressures can be equated like this and how manometers work. Coming to the next question. Here, the turbines in a hydroelectric plant are fed by water falling from a 50-meter height. Okay, delta H is equal to 50 meter. Assuming 91% efficiency for conversion of potential energy to electrical energy, right? Only eta is 0.91 and 8% loss of the resulting power and transmission. What is the mass flow rate of water required to power a 200 light bulb? So I want to impress on the thing, like generally whatever process happens in the nature, it does not happen with 100% efficiency. Okay, assume here the outlet is 200 watt, right? And this is the coming after the loss of 8%. This is some resultant power of something from something. Okay, and here also there is only 0.91%, like 91% efficiency here. So I say this 200 watt equals to, okay, what is power? Power is equal to work by time. Or you can also say this is energy. Fine. Here, this energy is the electrical energy, which is coming from the potential energy, which is 0.91 into potential energy. Okay, 0.91 into mg delta h. Here, this is mg is force into displacement. So this is the work done here. Work into efficiency, the total work by time. Here we don't know the mass flowing. So we consider this mass by time, sorry, yeah, mass by time as m dot. Okay, so this 200 is equal to m dot into, okay, here this 200 watts is coming from with a loss of minus 8%, right? So I would consider 1 minus 0.08. Again, this is 8%, so 0.08. Right? So I would say m dot into g delta h into 0.91 into 0.92, which is this 1 minus 0.08. Okay, and this g is we know already, 9.81 meter per second square, and this is in watt, so I am expressing everything in SI units only, and this delta h is 50 meter. On solving, we get this m dot is equal to 0.48 kg per second. Okay, so now we understand what is the power and how to work with these efficiencies. Okay, fourth question is we have studied the phase rule F is equal to C minus pi plus 2. Here, the C is number of components. This is number of phases. Okay. So what is F? Degrees of freedom. So when we see like there can be any system, for example, described by different properties like T and P. Okay, a system, normal system, one phase system we consider, it can be the state of the system is expressed using these values. Okay. And if there are like more than two phases, there will be like they are in equilibrium, or what is the liquid fractions inside the system, and what are the mole fractions in the gas. Okay, for the Y, it can be mole fraction or mass fraction. Okay, so what is the question is, how many variables do we need to know? So the minimum do we need to know so that we can tell what is the state of the system. Okay, consider here liquid water in equilibrium with its vapor. For this, if we solve, F is equal to, the component is only water. Okay, 1 minus pi. So there are liquid state and vapor state. 2 phases plus 2 is equal to 1. So we need to know at least one of the T and P here. And X and Y are anyway is equal to 1. So if, for example, we understand this, like if we know the pressure, we know the boiling point, right? For equilibrium system. If we consider a system like liquid water in equilibrium with a mixture of water vapor and nitrogen. So the gas is a mixture here. If we consider that, F is equal to two components, okay? Water and nitrogen minus two phases plus 2 is equal to 2. So we need to know at least 2 from these. Either T and P or T and X or P and X, anything like that. Sorry, X is not here, X is 1 here. Why? It can be nitrogen soluble in also water, then also you will have X and Y like that, okay? So if you know like, okay, P and Y, then you can say the boiling point, T, at the equilibrium point, okay? And similarly, for the liquid solution of alcohol in water, here also you have two components with its vapor, in equilibrium with its vapor, and two phases. Here also F is equal to 2. Okay, I think it's clear here. Coming to the next question. A small container has a gas at 5 pascals. It is placed in an evacuated space. So we have a container at 5 pascal, but outside it is vacuum. We know that generally when we express what is the work done on any, okay, here we are asked if the container is punctured here somewhere, the work done by the gas is what? Okay, so generally we see if we have something like a piston here and there is a force applied from external source. So we say work done on system, which is expressed as this force into displacement. Okay, actually it's a dot product. Okay, F bar into T bar. So when F bar and D bar are in the same direction, for example, this is compression happening, compression, then its positive work on system, right? This is also expressed as minus PdV. Okay, this minus is because when compression happens, the dV is negative. That's why this minus is used to make the sign convention agree with here, valid. Okay, so compression positive. So what we understand for the expansion, it is negative work on system. So here we understand because of the external pressure, the work is done on the system. When this is the case, it is completely vacuum outside. So there is no force from outside. So that's why here the work done is 0. Okay. It is desired to bring a certain change in the state of a system. State means the temperature and pressure there. Okay. By performing work under adiabatic condition, which is Q is equal to 0. And we have the first law, delta U is equal to Q plus W. Okay. And this is given 0. So amount of work is path dependent or path independent. Okay. Assume like we have two different states here. Okay. P and P. Generally, yeah, P1, P1, P2, P2. If we go from here to here, here to here, in different paths, we will have different we will have different amounts of work because the product of PV is like the work done there. Okay, when you are like gradually changing the pressure and the volume is also changing here. Okay, so in different parts we have different works. But since here Q is equal to 0 and delta U completely depends on the system properties, and we know that P1 even is generally a constant for some ideal gas, assume. Then here the delta U is constant always for any path. So it means that W is also constant here. So in this case, we would say the amount of work is path independent. Generally, it is dependent, but here it is path independent. Okay. Coming to this question, please don't worry of saying a very long question. We'll read it slowly. A horizontal piston cylinder arrangement is placed in a constant temperature path. So we write delta T is equal to 0. The piston slides in the cylinder with negligible friction and an external force holds it in place, okay, against an initial gas pressure of 14 bar. So there is a piston system, okay, and P1 is equal to 14 bar and B1 initial gas volume is 0.03 meter cube. The external force on the piston is reduced gradually and the gas expands isothermally as its volume doubles. And V2 is equal to 2V1. So, if the volume of the gas is related to its pressure so that PV at some time t is constant, what is the work done by the gas in moving the external force? So it is given PV is equal to constant, which is generally P1, V1 here. We already have those values. Okay. Now we say work dW is equal to minus P dV. On integration, it turns out integral from V1 to V2. And we don't know the pressure at each increment. Okay. So now we express this pressure as P is equal to P1 V1 by V. And using this here minus P1 V1 integral dV by V from V1 to V2. Okay, is equal to minus P1 V1 ln of V2 by V1, which is equal to 2 here. So we get work is equal to minus P1, which is 14 into 10 power 5 Pascal. Here it's mentioned bar into 0.03 meter cube into ln2. This gives us minus 29.11 kilojoules. Okay, here one more question is there. How much work would be done if the external force were suddenly reduced to its half, its initial value, instead of being gradually reduced? So, if P2 is equal to P1 by 2. So when the pressure of the system is suddenly reduced, now what pressure we have? Is P2 only, and this is equal to 7 bar. Okay, 14 bar it was there. 7 into 10 power 5 Pascal. So using this pressure only, we have work here. Okay, completely integral if we bring out P is minus integral P dV. This P comes out of the integral and we have minus 7 into 10 power 5 into V2 minus V1, which is 0.03 meter cube. So is equal to minus 21 kilojoules. So here we understand okay, 1 minute. Yeah. So we here understand that it was 21 kilojoules for the sudden change and 29 kilojoules for the slowly reduced gradually thing. So we can see where the two systems have difference. Okay, generally we write like this, right? V1 is here, V and V, 14 bar and 0.03, and V2 is more with P2 is half of this. Okay. So if we gradually decrease it, then it's like this. Understand? Then the work done is hold this. And when we suddenly reduce it, the work done is this much only. Okay. So this is lesser than the complete volume, complete this surface, complete work done in the first case. Fine. Okay. Coming to the last question we have here. Nitrogen flows at a steady state through a horizontal insulated pipe with inside diameter of 1.5 inch. Okay, you can convert this into meter if we are working completely with the SI units. Okay, here, okay, a pressure drop results from flow through a partially opened wall. Just upstream from the wall, the pressure is 100 psi A. Okay, here A means the absolute pressure. The temperature is 322 Kelvin. Okay, so just here it is 100 psi and T is 322 Kelvin and U is 20 feet per second. Right? The pressure just downstream is 20 psi A. What is the temperature here? Okay, it's like it's here mentioned as a wall. You can also assume if there is a small hole in a big pipe, what will be the temperature drop in this case? And also there is a lot of pressure drop also, we can see this. Okay, so coming to the system, we generally have two balances. The one is mass balance. Okay, we see the flow is at a steady state. Okay, so the mass balance gives us d m cv. The cv is says the control volume by dt is equal to, okay, I can write plus delta rho ua fs gives says flow stream is equal to 0. So this is 0 since it is at a steady state. Then rho 1 u1 a1 is equal to rho 2 u2 a2. We can also say this is a continuity equation, okay? And we say a1, a2 is same. Same area is being shared here. And this rho 1 is like m1 by v1. So the same mass will be flowing. So u1 by v1 is equal to u2 by v2. So we say u2 is equal to u1 v2 by v1. We generally say this as a specific volume also. Okay. And one more balance what we have is energy balance equation, okay, which is given by d mu cv by dt equals to q dot plus ws dot minus delta m dot into h plus u square by 2 plus gz. Okay, so we assume there is negligible change in potential energy and it's a steady state. There is no heat supplied or taken, no shaft work. So we say delta H is equal to delta U square by 2. Okay, so this delta H is given by Cp by molecular weight into delta T. Okay, is equal to U2 square minus U1 square by 2. Here Cp has units of joule per kg Kelvin. Okay. And molecular weight has a units of kg per mole. And the Cp is generally expressed as given in the question. Cp is equal to 7 by 2 R. And R has the units of joule per mole Kelvin. Okay. Now I think you have valid equation here. So as we have the equation that U2 is equal to U1 V2 by V1. It can also be expressed as U1 T2 by T1 into P1 by P2. Okay. So applying it here, we have the equation Cp T2 minus T1 by molecular weight equals to, okay, sorry for that. Here it is the negative sign is here. Okay, minus equals to minus u1 square. So T2 square by T1 is 322. You can see here also 322. Okay. And the Cp is 7 into 8.314. 7 into R by 2. This 2 and 2 got cancelled here. Okay, molecular weight of the nitrogen and 322 square into P1 by P2 is there, right? So that is 5 square minus 1. Now, here you see that this is a nonlinear equation in T2 and all other values are known. So generally, when you have like a simple equations like x1 plus 5 is equal to x2 and some x2 plus 3 is equal to x1, something like this, you can solve linearly with hand. Okay. And even if you have some polynomial x1 square plus 2x plus 1 is equal to 0, all these like you can solve using calculator or hand. But the what we have got is also actually a non-linear, second order polynomial. So I would suggest like further in this course you will get even more complex systems. Okay, you will have x1 into x2 equals to 2x1 minus 5, and one more thing, x2 square minus 2x1 x2 square is equal to 0. Something like this you will get, where you have to solve the nonlinear system. So I suggest you to go through the symbolic variables in MATLAB. Okay, here you can mention this equation is equal to whatever we have here, Cp by a molecular weight, T2 minus T2 is like x, okay, x minus some 322 plus what we have u1 square. It's generally we'll get on conversion, we'll get 36 meter square per second square. Okay, u1 square into 5 square x square by 322 square minus 1. Okay, and we use solve equation for x. Okay, when you solve this, it will solve for equation equals to 0. We'll use some methods like Newton-Raphson. Okay. Then on using this, you have got x is equal to one negative value is there and one positive value is there. In this case, realistically, if we see going till the negative temperature is too much difference. So we consider positive temperature, which we get as 321.6 Kelvin. Okay. Yes, I guess that is only that. Right. So here we understand how to use the mass balance and energy balance equations, right? So, and how to solve complex systems. So I hope all the questions are clear here, and I wish to meet you all in the next session every Saturday, 3 to 5 p.m. Thank you.